February 15, 2013, Chelyabinsk, Russia, 9:22 in the morning. People were driving to work. Kids were walking to school. Nobody looked up. Then the sky turned white. A fireball brighter than the sun tore across the atmosphere at 68,000 kilometers per hour. 17 seconds later, a shock wave hit the city like a wall of invisible force. Windows exploded inward. Roofs collapsed. Over 1,600 people were injured in minutes. And here's the part that should keep you up at night. Not a single telescope on Earth saw it coming. Not NASA, not ESA, not Russia's own space agency. Zero warning, zero time to react. A rock the size of a 6-story building, and we were completely blind.
Right now, as you watch this, there are over 2,300 asteroids officially classified as potentially hazardous. That's the official number from NASA's Planetary Defense Coordination Office, updated in early 2026. Potentially hazardous means two things: big enough to cause serious damage and close enough to Earth's orbit to matter. But here's what scientists privately admit. That number, it's only what we've found so far. Estimates suggest there are over 25,000 near-Earth asteroids larger than 140 meters that we haven't cataloged yet. 140 meters. That's bigger than the Eiffel Tower on its side, moving at 30 times the speed of a bullet. Space is not the empty, peaceful void that we like to imagine. It's a shooting gallery. And Earth has been in the target lane for 4.5 billion years.
Let's go back to Chelyabinsk, because this event didn't just injure people, it broke assumptions. Before 2013, the scientific community believed that events of this scale happened maybe once every 150 years. The Chelyabinsk asteroid was approximately 20 meters wide and weighed around 500,000 metric tons. It released energy equivalent to roughly 30 Hiroshima atomic bombs, and it didn't even reach the ground intact. It disintegrated at about 30 kilometers altitude. The explosion happened in the sky. And that's exactly why we missed it. Our detection systems at the time were focused on large objects, 140 meters and above. Objects under 50 meters were considered, quote, too small to worry about. Chelyabinsk proved that thinking was dangerously wrong. A 20-meter rock didn't need to hit the ground to shatter a city. To understand the threat, you have to understand what these things actually are. Asteroids are not just rocks floating in space. They come in radically different types, and that type determines how dangerous they are. C-type asteroids, carbonaceous, are the most common, dark, fragile, rich in water and carbon compounds. S-type asteroids are silicate, stony iron, brighter, more reflective. These are easier to track. M-type asteroids are the ones that should genuinely concern you. They're metallic, dense, iron and nickel through and through. An M-type asteroid doesn't crumble in the atmosphere like Chelyabinsk did. It punches straight through. Scientists also distinguish between monolithic asteroids, solid single bodies, and rubble piles, which are clusters of debris held together loosely by gravity. A rubble pile asteroid is arguably more dangerous to deflect because if you push it wrong, it breaks into dozens of smaller impactors. You turn one bullet into a shotgun blast. Composition matters. Trajectory matters, and in 2026, we still don't know the composition of most near-Earth objects we've detected. Let's talk scale, because this is where the numbers get viscerally real. 25 meters or smaller, localized destruction. Think a city block, a stadium, Chelyabinsk territory. 50 to 140 meters, regional devastation, capable of leveling a major metropolitan area entirely. The 1908 Tunguska event, likely in this range, flattened 2,000 square kilometers of Siberian forest. If that hit London, Paris, or New York, the death toll would be in the millions. 300 meters to 1 kilometer, continental-scale disaster. Tsunamis if it hits ocean. Shockwaves felt across entire regions. Years of climate disruption. 1 kilometer and above, civilization threatening. The impact winter alone could collapse global agriculture. 6 kilometers and above, mass extinction event. This is what killed the non-avian dinosaurs 66 million years ago. The Chicxulub impactor was estimated at 10 to 15 kilometers wide. Scientists have confirmed no object of that size has a significant collision probability with Earth in the next 100 years. But the smaller ones, that's a different conversation.
So, which asteroids are scientists actually watching in 2026? Let's look at the real data. Asteroid 2024 YR4, discovered in December 2024, briefly held the highest impact probability ever recorded for a known near-Earth object. At its peak, models showed a roughly 3.1% chance of Earth impact in 2032. That's not small. In asteroid terms, that's alarming. NASA and ESA immediately activated enhanced observation protocols. Telescopes across 6 continents were pointed at this single object. As of early 2026, additional tracking data has significantly reduced the probability, but 2024 YR4 remains under active surveillance. Then there's Apophis, 370 meters wide, which will pass Earth in April 2029 at a distance closer than our own communication satellites. Current models say Apophis will not hit in 2029, but the 2029 flyby could alter its trajectory enough to create new risk windows in later decades. Scientists call this a keyhole, a specific region in space that, if an asteroid passes through it, gravity sets up a future collision. Apophis will be the most closely observed asteroid in human history when it passes in 2029. It will be visible to the naked eye over Europe and Africa, a 370-meter boulder visible without a telescope. That moment alone will change how humanity thinks about this threat.
Here's the uncomfortable truth about our detection systems in 2026. We've cataloged roughly 95% of near-Earth asteroids larger than 1 kilometer. That's genuinely impressive progress. But for objects in the 50 to 140 meter range, the city killer zone, we've found less than half. Less than half. Part of the problem is geometry. Asteroids coming from the direction of the Sun are nearly impossible to detect with ground-based optical telescopes. Chelyabinsk came from the Sun's direction. That's why no one saw it. The other problem is funding. Global planetary defense receives a fraction, a tiny fraction, of what any individual nation spends on conventional military. In 2024, NASA's entire planetary defense budget was approximately $360 million. That sounds like a lot until you compare it to the annual cost of a single aircraft carrier. The Surveyor telescope, specifically designed to find sun direction asteroids, was approved and is targeted for launch in 2026. It represents the biggest leap in detection capability in a generation. But a telescope finds the threat. It doesn't stop it. And that's where the story gets complicated. September 26, 2022. NASA deliberately crashed a spacecraft into an asteroid at 22,000 kilometers per hour. This was the DART mission, Double Asteroid Redirection Test, and it worked. The target was Dimorphos,
a 160-meter moonlet orbiting a larger asteroid called Didymos. Before impact, Dimorphos completed one orbit around Didymos every 11 hours and 55 minutes. After DART hit it, that orbit shortened by 33 minutes. We moved a space rock with a spacecraft, on purpose. This was humanity's first successful planetary defense test in history. But DART was designed for a specific scenario: years of warning, a target we've already found, and enough time to build and launch a mission. What if we have 6 months? 2 months? What if we find the next Chelyabinsk 3 days before it arrives? That's where the honest answer becomes uncomfortable. Right now, for short warning scenarios, our options are severely limited. Nuclear deflection, using a nuclear detonation near an asteroid to push it off course, remains the most powerful option on paper, but it requires international treaties, rapid launch capability, and political consensus that does not currently exist.
Let's be precise about where planetary defense actually stands in 2026. The good news, we have proof of concept. DART showed kinetic impactor technology works. ESA's Hera mission is now studying the Dimorphos impact site in detail. The bad news, we have one proven method, tested once on a small asteroid under ideal conditions. We have no rapid response launch infrastructure, no asteroid-specific warhead system, no international unified command structure for a real planetary emergency. In 2021, NASA ran a simulation exercise called PDC 2021, Planetary Defense Conference. Scenario: a newly discovered asteroid with a 1 in 100 chance of impact, 5 years out, 100 meters wide. The result: even with 5 years of lead time, the simulated response struggled with international coordination, mission funding timelines, and technical uncertainty. 5 years, and it was still messy. Now imagine the same scenario with a Chelyabinsk-type object and 6 hours of warning. Scientists don't say this to frighten you. They say it to make the case for urgency, because the solution is buildable, fundable, and achievable. We just haven't chosen to fully build it yet.
So where does this leave us? What is the actual bottom line in 2026? The probability of a civilization-ending asteroid impact in the next 100 years is genuinely low. Scientists are confident in that assessment. But the probability of a regional-scale impact, something that destroys a major city or coastline, is not negligible, not zero, not even close to zero. The Chelyabinsk class of events, 20 to 50-meter objects, statistically happens somewhere on Earth every few decades. We've been lucky where they've landed. The tools exist. The knowledge exists. The DART mission proved we can act. The NEO Surveyor will soon show us what we've been missing. What doesn't fully exist yet is the global coordination, the sustained funding, and the political will to treat this as the infrastructure problem it actually is. Not a Hollywood disaster movie, not a theoretical science exercise. An infrastructure problem, like building levees, like maintaining power grids, that requires consistent investment over decades. The asteroids don't care about election cycles or budget negotiations. They run on orbital mechanics, and orbital mechanics is indifferent to human politics. If this video made you think differently about what's above us, share it, not for the views, but because public awareness is literally how planetary defense gets funded. The sky isn't falling, but it has fallen before, and the only reason it won't fall again is because people decided that knowing was worth the effort. Be one of those people.